Part 4, which is stoichiometry, which is from the German stoichi and metron, which is to measure amounts. And that's where you get the most interesting name. And this is the part that drives people crazy because it's actually pretty straightforward as long as you follow the rules. Well, what are the rules? Well, stoichiometry are calculations based upon the species associated with chemical reactions. So, as long as it's in the chemical reaction, you can relate it to each other. So, for example, we talked about going to grams and moles, etc. Now, one major important thing is that because you are going through an equation, you must have the units in moles. You cannot compare grams to grams. You have to compare moles to moles because these are all set up based upon either atoms or moles, okay, because it's a counting number. So what we're going to do is convert to grams to moles, and then we're going to go from A to B using the equation. And then if you have moles of B and you want grams, you're going to go back using, again, the atomic weight, the formula weight, or the molecular weight. Stoichiometry is one of the simplest things, but it's really, really simple, which means it's really, really hard. And there's an old phrase that says it's as easy as taking candy from a baby. Well, if you think taking candy from a baby is easy, go find a toddler, give him a sucker, and try to get it back. It is not easy until you know the trick. So I'm going to try to show you the trick on stoichiometry. Now, the trick really is follow your equation and follow your units. Your units will tell you where to go, and your equation will tell you the numerical relationships. Now, here's the thing. We have A, B, C, and D, and notice we have different coefficients. So when we compare our equation comparisons, we're going to use whatever's in the equation. So A to C is 1A to 3Cs. If we were doing B's to D's, then we would use 4 and 2. Okay? If we were doing, and we can do any ones we want, if we were doing C to A, well, we already did that one, C to B, and we have the 3C and the 2B. Doesn't matter whether the B's on top or bottom if you're comparing it just at mole level, but it does matter that the coefficient goes correctly. What is critical is follow your units. You do not have to have a clue as to what you are doing. But if you follow your units, they will tell you where to go. Okay? So I always start with where I'm going because sometimes I get lost in a process. So we're going to start with the amount given. This is always the amount given. You don't want to use a conversion factor. And so notice that the grams of A are going to cancel. So that leaves you grams to moles. This is in a molecular weight, an atomic weight, a formula weight, whatever. So your grams canceled. Now your moles of A canceled. This goes through the equation. So you're relating moles of A to moles of B. So then if we want to go back to grams, we use atomic weight, molecular weight, formula weight. And your moles of B cancel. So assuming your numbers are correct, your value is correct. Then you have to worry about significant figures, but more about that in just a minute. So the point being is numbers on the tops are multiplied, numbers on the bottom are divided. Now, what that really means is make sure you got your order of operations correct in your calculator. Now, you can do it with the parentheses, or the easiest way is the line, and if you'll notice, we're canceling and all the units are gone and we're left with our values. And the trick is cancel the units. It's been years since I've done things like physics. But there are certain physics problems that are a little complicated, take me a minute, but some of them are real simple. I don't know what I'm doing, I just make my units follow. If you put in extra units, big deal. As long as you don't make the units up, it's kind of like circling the block, trying to find a house, a business, whatever. You can go around 2 or 3 times. That doesn't change the fact that you're going to get there. It may take you a little longer, but that's okay. All right, so first things first, here we go. We're going to do the first stoichiometry problem. This is sucrose being metabolized and according to this reaction. So the first thing we're going to do is balance this. So we have 12 carbons, we have 1 carbon. So let's put the 12 there. So that balances our carbons. Remember the rule, hydrogen and oxygen last in that order. So here we have 22 hydrogens, we have the hydrogens here, and we have 11 there. So that gives us the same. Now, if we look at it on the reactant side, we've got 11 and we've got 2. Oh, that looks like fun. And then over here we have 24, 2, and 11 again. So wait a minute. If we let this 11 take care of this 11, then we can let this 12 times 2 take care of that 12 times 2. So sometimes when you balance, if you look at patterns, your life is easier. Okay? So we did the balance, we balanced the equation. I don't know where that 0 came from, but let's ignore it. Okay, so then the next question is how much CO2 in grams. So how many grams of CO2 are produced when 35.7 grams of sucrose is reacted? So this is the amount given. So we're going to start with it. So 35.7 grams. And I don't really want to write sucrose out, so I'm going to call it SUCR. And you can do that as long in your work, etc., as long as I know what you're calling stuff. And so if we calculate the molecular weight, we end up with 342.308 grams of the sucrose, equal to 1 mole. Now notice that the molecular weight, atomic weight, empirical weight, is a function of 1 mole. It has no bearing on the equation. So don't even worry about how many moles you have yet. All you're doing here is converting from grams to moles. Okay, that's all you're doing. So at this point in time, my grams of sugar have canceled. Finish writing there, moles of sugar. Well, I know that I'm going to need moles of sugar here, sucrose, but I don't want moles of sucrose. I want CO2. So I'm got to relate moles of CO2 to moles of sucrose. Wait a minute, we do that with our equation. Okay, so according to our equation, I got a 12 here and a 1 there. Okay, so my moles of sucrose are gone. Notice as I cancel, I'm canceling the units, but I am not canceling the numbers. And we find out that 1 mole of CO2 is 44.011 grams of CO2. So our moles of CO2 cancel. Now, we would take 35.7 times 1 divided by 342.308 times 12 divided by 1 times 44.011 divided by 1. Do you have to multiply and divide by 1? No. But it's a good idea to do it mentally so that you know you've covered all your bases. So we end up with 55.07996 grams. Okay? So, looks good. That's our answer, right? Well, kind of. But we got to look at our significant figures. Well, if we go back, this is 3 significant figures. This is lots, or 6. Okay, this is moles out of the equation, so that's infinitely many, and we're at 5 significant figures. So we're going to report it in the least number of significant figures for the math. So it's 55.1 grams of CO2 generated. Okay, because we don't worry about significant figures until we get to the end. Now, the second question says determine the mass of O2 when 12.3 grams of water is produced. It doesn't matter whether you're talking about 2 reactants, 2 products, reactant, product, product, reactant, whatever, as long as you go through the equation. So here again, we want the grams of O2. That tells me where I'm going. I'm going to start with the amount given, which is 12.3 grams of water. Well, if I'm converting water to oxygen, I have to go through the equation. So I need to convert my water to moles. And 1 mole of water is 18.016. And then I've got to have my moles of water, and I'm going to moles of oxygen. So if I look at my equation, I got 12 here and 11 here. And I want the grams back. If I had just asked for moles, we'd be done. So 1 mole of oxygen is 31.9988 because it's the O2 4 grams of oxygen. Now, if you canceled as you went, which I should have done, you end up with 23.832466 grams. And again, you're looking at it significant figure wise, we have 3 significant figures: 5, infinitely many, 2, 4, 6. So we were going to report it in the smallest. So it's 3 significant figures. So it's 23.8 grams of O2. Voila! We have just worked our first stoichiometry problem. Take a few minutes, look over it. It's not that bad if you take it apart and look at just the steps. Think about taking the steps to go into your house. You may have to, get out of the car, walk up a sidewalk, open a gate, open a front door, go up steps, not go up steps, go down steps, any variety of things, and that's the same. Okay, so the next problem we have, and for entertainment value, I'm going to change color. Aluminum sulfate reacts with plumbous nitrate according to the following reaction. Okay, balance the equation. So the first things first. So we'll start with lead. We have one lead. Life is good. The nitrate is not changing, so staying as an entity. And wait a minute, we have 2 here and 3 here. 2 and 3 are not equal. So the only way to equalize them is to figure out the lowest number that both of them go into, which happens to be 6. So that means I would need to multiply this one by 3 and this one by 2. Wait a minute, that messed up the lead. So let's go back. We have now 3 leads, so we'll need 3 leads here. So we have 3 leads. We have 6 nitrates. 3 leads, 6 nitrates. We're good there. The only thing that's not balanced are the sulfates. We have 3 sulfates here and 3 sulfates there. Well, that was convenient. And we have 2 aluminums and 2 aluminums. So that balanced itself as we went. Okay. So how many milligrams of aluminum nitrate are produced when 895.23 milligrams of lead nitrate react with excess aluminum sulfate? Wow. Okay. Notice again we're using milligrams. Now at this point in time, you can either show me the work by doing like 895.23 milligrams, and 1,000 milligrams is equal to 1 gram, or you can just go ahead and do it in your head, whatever makes you happy. So we're actually going to need milligrams of aluminum nitrate when we get it out, but we still have to convert to moles. Okay, so I'm going to go ahead and do the math in my head. 8.89523 grams of lead 2 nitrate. And first thing we need to do is convert it to moles. So there have to be 331.208 grams of lead nitrate, lead 2 nitrate, per 1 mole of lead 2 nitrate. Now we'll take a brief station identification. We're going to cancel that first, so we're left with moles of lead nitrate. Where did I get the 331? Well, I took my periodic table. I have 1 lead, 2 nitrogens, and 6 oxygens. I added the mass together, and that gave me the formula weight here. So at this point in time, I've got moles of lead nitrate, which I want to go away. But what I'm really looking for is moles of, what am I looking for? Oh, aluminum nitrate. I told you I got lost in these problems. Okay, so what are my numbers? Well, if I go look, lead nitrate is a 3. Aluminum nitrate is a 2. Okay, so my moles of lead nitrate are gone. I'm now left with moles of aluminum nitrate. I wanted grams, so 1 mole of aluminum nitrate. Yeah, I know, I really want milligrams. More about that in just a second. Is equal to 212.994 grams of aluminum nitrate. Remember, I just took 1 aluminum, 3 nitrogens, and 6 oxygens to get me there. But I don't want it in grams. I want it in milligrams. So I know that 1 gram is equal to 1,000 milligrams. Okay, so every number on top is multiplied. Everything is divided. So 0.8952 times 1 divided by 331.208 times 2 divided by 3 times 2, 12 divided by 1, and then multiplied by 1,000. Okay, so this gives us a whopping of 383.80437 milligrams of aluminum nitrate. Now, we're good to go, right? Nope. So let's look at significant figures. We have 4 significant figures here, 6 significant figures here, infinitely many here, 6 here, and this is metric conversion. So we're going to report it in the smallest, which is 4 significant figures. So it's 383.8 milligrams. It's actually really simple. As long as you convert the grams to moles, run it through the equation, and then pull it back out. Okay, so how many grams of aluminum sulfate were needed to produce 9.86 grams of lead sulfate? Okay, so we're in grams of aluminum sulfate. What's aluminum sulfate? SO43. To produce 9.86, again, you use the amount given of lead to sulfate. And where again, we'll have to convert it to its molecular weight, 266 grams of lead sulfate per 1 mole of lead sulfate. Remember, we need to start with the grams and convert it to moles so that we can take it through the equation. Because we have moles of lead sulfate, 2 moles of aluminum sulfate, or as the British like to say, aluminium. Okay, and if we look at the equation, this is a 1 and this is a 3. So our moles of lead are gone, and 1 mole of aluminium sulfate is equal to 342.15 grams of aluminum sulfate, which gives us a value of 3.70807 grams. But again, we're going to look at our significant figures. So we would report it in 3 significant figures, 6 significant figures, infinitely, 5 significant figures. So we're going to report it in 3 significant figures. So it's 3.71 grams. Now, if that wasn't an 8 behind the 0, it would report it as 3.70 because you still have to give the 3 significant figures regardless. Okay, so we've worked 2. We can take this another step in terms of we can work it with respect to given compounds where we have to generate a formula. Now, I tend to not do this on a test with the stoichiometry because if you mess up the formulas, then it messes up the entire equation. But this is a good exercise to review your naming skills. Okay, upon being strongly heated, ammonium nitrate. So ammonium nitrate, when it's strongly heated, that's the delta, decomposes into nitrogen gas, oxygen gas, and water vapor, which is gas. If 68.4 grams, so this is solid, decomposes this way, how many grams of nitrogen and how many grams, not of O2, of water are produced? Okay, well, first thing first, I've got my components. I don't have it balanced. Okay, so in order to balance it, I've got 1 nitrogen on the reactant, 2 nitrogens on the product, so we'll put a 2 there. No, we won't. We already had 2. You're like, wait, there's 1 nitrogen here. Whoops, there's 1 nitrogen here and 1 nitrogen there. So 2 and 2 were good. So then we move on to hydrogens. We have 4 hydrogens on the reactant side. We need 4 hydrogens on the product side. Okay, so that brings us to 2 plus 2 is 4 oxygens on the product side and 3 on the reactant side. So 3 is an odd number, 4 is an even number. So we're going to have to go back and double our original. And in order to erase that, I had to take out more than I wanted. So this is a 2. That means we now have 4 nitrogens. Okay, we now have 8 hydrogens. So now we have a total of 2 times 3, which is 6 oxygens. And if you look at it, we have 4 from water and 2 from O2. So we're actually balanced now. So here we go. We want grams of nitrogen. We're going to do 68.4 grams of ammonium nitrate. First thing we have to do is convert it to moles. 80.0436 grams of ammonium nitrate is equal to 1 mole of ammonium nitrate. And when we're looking at it, 2 moles ammonium nitrate goes with 2 moles of nitrogen. 1 mole of nitrogen is equal to 28.0134 grams of nitrogen, which gives us a whopping 23.9384 grams, which we're looking at it is 3 significant figures. So it's 23.9 grams. Okay, now to look at it slightly differently is let's do the grams of H2O. So if you'll notice, this first step and the second step are going to be the same. So it's 68.4 grams of ammonium nitrate, 80.0436 grams of ammonium nitrate per 1 mole of ammonium nitrate. So those are actually the same. Now here's where it starts to differ. You still have the 2 moles of ammonium nitrate because the 2 came from the equation. And on top, you're looking for water, so you're needing the moles of water. And if you look at the equation, that's 4. So these start to differ. This is where we start to differ. Now, if you had the end product, that would be the same, but you don't. We're doing grams of water. So that's equal to 30.79058, which, again, this happens to be three significant figures. It won't always be three significant figures, and that's 30.8 grams of water. So my recommendation is you take a look at it, and you look at the next one. You look at the previous one, and you look at how they're alike and how they're different, and that usually helps tremendously. Okay? Now, that brings us to the next question, or the next item in stoichiometry, which is the limiting reagent. A limiting reagent is exactly what it says. It's whatever limits the reaction. And when we say it limits the reaction by running out. So in this situation, we're going on a picnic and we're going to make sandwiches. Which one's the limiting reagent? Well, you look at it and it's like 5 slices of bologna. Obviously, it's the bologna. No. So if the first sandwich I want you to make is composed of 1 bologna slice plus 2 slices of bread, then how many sandwiches can you make? Well, you can make 4 sandwiches, assuming I can spell sandwich. 4 sandwiches, okay? And the bread runs out first. So in the first case, in your first sandwich, your limiting reagent is your bread. Okay? But we thought it was the bologna. Okay, let's make the second sandwich, because I'm a meat kind of girl. So when you make sandwiches for me, assuming I can spell sandwich, I want 2 slices of bologna plus 2 slices of bread. So when we do it that way, then we're actually only going to be able to make 2 sandwiches, because now my limiting reagent is now the bologna. So the question is how do you know what's your limiting reagent? Well, it's actually really easy. It's the equation. The equation is what dictates what you can and cannot have and stop at. Because it is a stoichiometry problem, you have to go through the equation. You can't just look at it and say, oh, I got 5 slices of bologna, therefore it's not going to be the limiting reagent. In chemistry, we don't play with bologna. We play with compounds. But if we look at 1 gram of sodium metal versus 100 grams of sodium versus 100 grams of gold, which one's which? Well, it depends on the equation, but let's assume they're 1 to 1. That many grams of sodium is 4.3 moles, but that many grams, same number of grams of gold, is only 0.51 moles. So if you're 1 to 1 moles, you got a lot more sodium than you do the gold. So therefore, if it's 1 to 1, it'll be, the limiting reagent will be the gold. But if it's 5 to 1 sodium to gold, then is 5 to 1 going to work? No. 10 to 1. Then it will flip over. The easiest way, and there are other ways to do this, so don't get me wrong, there are multiple ways to do this. However, the safest, least getting in trouble, is to select a product and to go through the equation and to figure out a particular product. Now, the trick to that is occasionally you're asked a further question about species, and so that's a good time to pick a particular product. But let's pick a product. Okay, so one way to produce hydrogen sulfide gas is by the reaction. Okay, so we have a reaction here. We have 12.6 grams of HCl with 15.6 grams of iron 2 sulfide. How many grams can be formed? What is the mass of the excess reagent remaining? And basically what it's asking is what's the limiting reagent. Okay, now I wrote this underneath the equation. If you like to do that, that's fine. If you don't like to do that, that's fine. So the trick is that we need to pick a product. Well, in this particular case, we were asked for a product, so let's pick that product. Okay? So first thing we're going to do is we're going to look for grams of H2S. And the first time is we're going to start with, and it doesn't matter which one you start with, grams of HCl. When you do this, you're going to assume that you have excess FES. Now, what does that mean? Well, if you have excess, that means you have way more than what you need. So if you're in the kitchen and you're making brownies and you need a cup of sugar and you just bought a 25-pound bag, then you would pretty much feel comfortable saying that you have sugar in excess. Okay? So we're going to work this through, and we're going to work it like a straight stoichiometry problem. We don't care what the iron 2 sulfide is doing. So we know that 1 mole of HCl is equal to 36.4606 grams of HCl. And then we're going to go through the equation because we've gotten rid of the grams. Moles of HCl. We're looking for moles of H2S, so let me go look at it. So this is 1, this is 2. 1 mole of H, and I've canceled my grams there, mole of H2S is equal to 34.0818 grams of H2S, which is equal to 5.888969 grams. Okay. Are we worried about stoichiometry? Not yet. No, not yes. Well, that was wrong. We're worried about stoichiometry. We're not worried about significant figures. So let's do it all again. We're going to look for, again, the grams of H2S. This is critical because you want to compare apples to apples. You don't want to compare apples to steaks or bananas or guavas, whatever. So on this one, we're going to assume that we're in excess for the HCl. So we're going to deal with the iron 2 sulfide, which is 15.6 grams. And we're going to convert it 87.913 grams of FeS per 1 mole of iron 2 sulfide. And so moles of iron 2 sulfide per moles of H2S. Well, if we look at it, that's going to be the same, and that happens to be 1. And we got rid of everything. We're now to moles of H2S, and guess what? This is the exact same molecular weight as it was up ahead. Okay? So that was simple. So when I work problems with limiting reagents, I tend to pick the same product. And I tend to set it up and then solve it because if you use a TI-84, you can do a second function enter and you can get the entire formula. The only trick to that is typos will get you in trouble. So you end up with 6.047757 grams. Okay, so now we have two different amounts. And so if we look at it, this is the smaller amount, right? Which means that if we use all the HCl, we're only going to generate 5.88 grams. 9 grams, okay? So that means that the HCl will run out first. That means it is the limiting reagent. So it limits how much iron 2 sulfide you can form. So now we go back and we look at significant figures. And so we have 3 significant figures, so it's 5.89 grams. So the most we can generate with these two amounts is 5.89 grams of H2S. Okay? So how many grams of H2S can be formed? Okay, good. We're done with that. Okay, what is the mass of the excess reactant remaining? Okay, so this one is we need the excess iron 2 sulfide. So what's left? So what that really means is how much did we use? So how many grams of iron 2 sulfide did we use? That's what we're looking for. So we know our limiting reagent is hydrogen chloride. So we go back 36.4606 grams of HCl per 1 mole of HCl. Now in this particular case, since we're trying to figure out what we will use 2 moles of the HCl. And again, our units cancel. But this time, oops, I forgot the grams. We're going to 1 mole of iron 2 sulfide. Now the beauty of this particular problem is we've pretty much worked all the hard math like the formula units. So now we're moles. So 1 mole of iron 2 sulfide is 87.913 grams of iron 2 sulfide, which comes out equal to a whopping 15.19042 grams. Which, using significant figures, we use 15.2 grams were used. That wasn't the question. The question was, what is the mass remaining? So the remaining amount is equal to what you started with, which was 15.6 grams, minus what you used, which was 15.2. So that means I have a whopping 0.4 grams left. Now, if somebody looks at it and go, "What? Wait a minute, that's not right, significant figures." It actually is, because according to the math, you're using addition and subtraction, which means you count decimal places. So in this particular case, the final answer comes down to be 0.4, which is one significant figure. Okay. So the next thing we have when we're doing the stoichiometry is percent yield. Percent yield is relatively simple in terms of it wants to know how much did you actually produce. When you go to a lab and you run a reaction, some reactions go to completion easily and plentifully, others do not. And so, especially organic, but that's for you later. So what we need to know is how much did you actually get? Well, the theoretical is whatever is on paper. How much in theory is the perfect amount that you could get. Experimentally is what you actually got. Now, here's the thing. Can you get a percent yield greater than 100? Actually, yes. Because think about it, in lab, if you mix 2 reactants together and you end up with some product, but you didn't get rid of all your reactants, then you have an artificial number there. So be careful, because it is always theoretical on the bottom and experimental on the top, not the biggest number on the bottom. Okay, I'm not going to lie. I have a nasty habit of making percent yields be higher than 100. Okay, just be aware. So how do we work this problem? Well, let's go back to problem 2, where we had the aluminum sulfate and the lead nitrate. Okay, we had got this answer here. I didn't make this answer up. We got it. So now, if you'll notice, we got the C. We did C. Now we're at D. What's the percent yield if that many grams of aluminum nitrate was produced? Okay, so remember, percent yield is equal to experimental over theoretical times 100. Don't forget the times 100. Not going to lie. Occasionally I do that. So in this particular case, we're told that experimentally we had 0.2453 grams. Theoretically, we calculated that amount. Wait, that's milligrams. Okay, does it matter whether you use milligrams or grams? Nope. But since I already wrote that in grams, I'm going to go ahead and write this one in grams as well. Times 100, we would get 63.9135%. Both of them are four significant figures, so we'll report it in four significant figures, so it's 63.91%. Now, you could have done exactly the same thing with milligrams by putting 245.3 milligrams divided by 383.8 milligrams times 100. You're going to get the exact same number. All you did was converted them both to the same unit. Okay? Doesn't matter which unit you use. It's strictly a function of what you want to do. Okay, so we'll work, I think, one more equation here. Let me switch to that. This is how I tend to ask problems on the test. That may not be true this semester because of teaching online, but it may be. I may do pieces, parts. Okay, so on this particular case, we've got an equation here, a balanced equation. All right, so we have one copper, one copper. Oh, life's good. We have two chlorines. We have no chlorines. Oh, yeah, wait. There's a chlorine. Sorry. So we're going to need two chlorines here. So then we go one potassium, two potassium. So we have two potassiums there. So that was with two iodides on the reactant side and three iodides on the product side. Oh, man. If we have an odd and an even, what do? Well, first thing we do is we go back and we erase everything. And then we think, okay, double. So first thing we got to do is make sure that our odd goes even. So there's our odd iodide. So let's go do it first. So it's 2. So we have 2 iodides there and 2 iodides there. So we have 4 iodides there. So now that messes up the potassium. We have 4 potassiums. We need 4 potassiums. Okay, we have 4 chlorines. We need 4 chlorines. And we have 2 coppers and 2 Oh, wait, that was beautiful. Okay, so we now have a balanced equation. All the numbers are in. This is a 1 here at the in front of the iodide, so it means that's the lowest. So we did that one. So then the question is if 65.78 grams of copper chloride reacts, okay, which species is the limiting reagent? So we're going to need a product. We have 3 products to choose from. So I like working efficiently, shall we say. Not doing extra work. So if I come down here, I'm told that we have so much KCl produced in the reaction. So that means this is going to be my experimental value, and I've got a % yield. So let's make my life easier. Let's solve for KCl. Now, we could pick any product, but by solving for KCl, then we've already done part of the work we need for C. If we don't solve for KCl, we find the limiting reagent, and then we have to do the stoichiometry again, which some people prefer. It is strictly up to you. So we're going to start with 65.78 grams of copper 2 chloride, which means we're going to assume excess Ki. So we're going to set this up, and we get 134.45 grams of copper 2 chloride per 1 mole of copper 2 chloride. Okay, moles of copper 2 chloride go on the bottom. So we have 2 of those based upon the equation. We're going to KCl, so we need 4 moles of KCl. and 1 mole of KCl, my moles are canceled there, is equal to 74.551 grams. Now, guys, something I want to point out to you is, where did I get the KCl? I took 1 potassium and 1 chlorine and I added it together. I have a habit of when I start an equation, I just go ahead and find all the molecular weights. I may not use them, but I just find them because it's faster. In a test situation, you can do that, or you can find the ones you need as you go. But I want you to be aware that these problems are working pretty fast because I've done some of the prep work. So as you work these problems, give yourself some time because they're going to take you longer because the prep work won't be done for you. Okay? So I'm going to set this second one up because I'm going to use my fun calculator trick. So we're going to solve for grams of KCl, but this time we're going to use excess copper 2 chloride. So we're going to start with the other reagent, 93.49 grams of Ki. And potassium iodide is 166.0033 grams of potassium iodide per 1 mole of potassium iodide. My potassium iodide grams cancel. I'm left with moles. Moles potassium iodide. And I go up how many moles? 4 moles to 4 moles of potassium chloride. And this number is the same, so the beauty of it is I don't have to recalculate it. If you've made a mistake, then you'll make the same one twice. It won't change your limiting reagent, it will change your value. Okay? So now I'll pick up my calculator, 65.78 times 1 divided by 134.45 times 4 divided by 2 times 74.551 divided by 1, and do the math. So I'm going to end up with 72.947 grams of the potassium chloride here. I get 41.9857 grams. Now, before we go any farther, if you were looking at it going, wait, but the Ki, I got more of it, so it's obviously not going to run out first. Wrong. By actually a chunk on this one. Why? 2 reasons. The molecular weight or formula weight of the potassium iodide is much greater than the copper. So therefore, your larger amount breaks down fewer moles. And your ratio is 4 to 4 or 1 to 1, not 2 to 4 or 1 to 2. So that makes a huge difference. So this is the smaller amount, but the word limiting reagent involves the word reagent. So the limiting reagent is a reactant, not a product. So it's the one that's going to run out first. So that would be this one right here. So it's going to be Ki. That means then we go back and look at significant figures. We are using 4 significant figures. So we get 41.99 grams of the KCl is generated. And that is ideal, so that's theoretical. So percent yield, remember, is going to be experimental times theoretical times 100, which means that in the experiment we're told we got 32.87 grams. In the theory we got 41.99 grams times 100. And that gives us a whopping 78.28%. I'm not really sure what the farther numbers are, but I stopped there because that's actually 4 significant figures, which is all my percent yield. So life is good. And we just worked a problem. Again, stoichiometry sounds awful, and a lot of people like to freak out. But if you take the time and study it and think, what are these things are like the others, then you'll figure out quickly that stoichiometry is really not that bad. And this test, more than any other test, is the one that I guess proves whether you've worked and got the material or not, because the stoichiometry is the hard part. And if you follow your units, then you are golden. Okay, the next one, this is an extra problem. The key is posted on D2L Daylight, which is switched to Bright Space. It's the name du jour. So this whole thing is worked. Notice we have balanced the equation. This is a simple stoichiometry right here. This is a simple stoichiometry. This is a limiting reagent. When you start with two amounts of the reactants, both separate reactants, it's a limiting reagent. This is a percent yield. So I would assume on the test I will have multiple options there. I usually restrict it to giving you a balanced equation just because, let's be honest, in D2L you can generate numbers, but you can't if your equations are variable. So be prepared for those there. But this one has worked. I'm not sure that this one has worked as a video. I don't think it is. But there are several of them worked in the video folder labeled stoichiometry. And there are a bunch of them up, and there are a bunch of them in the back of the book. And more than any other ones, the more you work, the better you're going to get. And we are done with this chapter. We will start the next chapter next. Well, that's kind of obvious. So take your time. I will warn you right now. These videos will be going up very shortly after your last exam. Take a break, a day or two, but then start. And I will warn you now, these are like driving. It is very easy to drive from the back seat, but it is critical that you take your turn behind the wheel and work the problems. Do not wait until the last minute. You have a couple weeks to play with these and work through. Please do the math, because until you actually work the problems, they're hard until you get the tricks. Okay? So we're done with chapter 3.